Have you ever wondered why your computer sometimes feels slower than it should, even though the specifications look impressive on paper? Or why certain tasks seem to complete in the blink of an eye while others drag on endlessly? The answer might be hiding in plain sight, inside a technology that's been quietly working behind the scenes for over 2 decades. Today, we're going to uncover a secret that Intel doesn't always advertise clearly, a trick that makes your processor smarter without making it more powerful. Before we dive deep into this fascinating world, if you appreciate content that helps you understand the technology you use every day, consider subscribing to our channel. Your support keeps us bringing these stories to light. Let me tell you about a problem that existed at the turn of the millennium. Engineers at Intel were staring at a peculiar challenge. They had built processors that were incredibly fast, clocking in at speeds that seemed impossible just years before. But there was something deeply frustrating happening inside those chips. Like a master chef with a fully equipped kitchen who only uses half the utensils, these processors were leaving valuable resources sitting idle, doing absolutely nothing while waiting for the next instruction. Imagine a restaurant where the grill is blazing hot, but the chef is waiting for ingredients to arrive from the pantry. The heat is there, the potential is there, but nothing is cooking. This wasn't just a minor inconvenience. It was a fundamental waste of capability. Every clock cycle that passed with execution units sitting empty represented lost opportunity, wasted silicon, and performance left on the table. The traditional solution had been straightforward: add more physical cores. If one core can't handle the workload efficiently, why not add 2, then 4, then 8? This approach worked, certainly. Multi-core processors transformed computing, allowing your laptop to juggle dozens of applications simultaneously. But it didn't solve the underlying issue. Even with multiple cores, each individual core still had moments of idle time, gaps in the pipeline where nothing productive was happening. The engineers needed something different. They needed a way to squeeze more work out of each core without fundamentally redesigning the entire processor architecture. The solution they developed was called hyperthreading, and it arrived in 2002 with the Pentium 4 and Xeon processors. Think of it as a magic trick, but one based on solid engineering principles rather than illusion. The concept was elegant in its simplicity. Instead of letting a single core sit partially idle while waiting for one instruction stream to complete, why not give it 2 streams to work on simultaneously? Here's how the magic works. With hyperthreading enabled, each physical core presents itself to your operating system as 2 separate logical cores. Your Windows or Mac system sees a dual-core processor and interprets it as having 4 cores available. Now, before you get too excited, these aren't real cores in the physical sense. You can't suddenly claim your computer got twice as powerful overnight. What happened is more subtle and, in many ways, more clever. Each physical core can now juggle 2 independent threads of instructions, switching between them rapidly to keep those execution units constantly fed with work. Imagine you're reading 2 books simultaneously. Not literally at the same exact moment, but alternating between them so frequently that you're making meaningful progress on both. When you hit a complex passage in the first book that requires you to pause and think, you switch to the second book and keep reading there. By the time you return to the first book, you've processed that complex passage mentally and you're ready to continue. Your brain's processing power hasn't doubled, but your efficiency has improved dramatically because you're eliminating idle time. That's essentially what hyperthreading does for your processor. The operating system gains remarkable flexibility from this arrangement. Those virtual cores can be assigned tasks independently, interrupted individually, and scheduled just like physical cores. A video editing application might send one thread to logical core 1 and another thread to logical core 2, never realizing that both threads are actually sharing the same physical hardware underneath. The processor manages the complexity behind the scenes, deciding moment by moment which thread gets access to which execution unit, ensuring that as little silicon as possible sits idle. Let's talk about where this technology truly shines. Picture a professional video editor working on a documentary. The editing software needs to decode compressed video, apply color correction, render transitions, process audio tracks, and update the preview window, all simultaneously. This is a massively parallel workload with dozens of independent tasks that can proceed without waiting for each other. A quad-core processor with hyperthreading, appearing as 8 cores to the system, can spread these tasks across all available threads. The performance improvement can be substantial, sometimes approaching 30 to 40% compared to the same processor with hyperthreading disabled. Software developers compiling large code bases see similar benefits. The compilation process involves analyzing thousands of files, checking syntax, optimizing code, and linking libraries. These operations can largely happen in parallel. When the compiler splits this work across 8 logical cores instead of 4 physical ones, build times can drop significantly. The same applies to three-dimensional rendering, scientific simulations, data compression, and any task that can be broken into many smaller, independent pieces. The more threads you can throw at the problem, the faster hyperthreading helps you solve it. But here's where the story gets more nuanced. Not all work benefits equally from this approach. Consider the simple act of opening a web browser or launching your email client. These are relatively lightweight operations that complete in milliseconds, regardless of how many cores you have. The browser doesn't generate enough parallel instruction streams to fill 8 logical cores. You might use 2 or 3 cores briefly, and the rest sit completely idle whether hyperthreading is enabled or not. The virtual cores provide no advantage because there simply isn't enough work to distribute. Gaming presents an interesting middle ground. Modern video games are becoming increasingly multi-threaded, but they're not uniformly parallel like video rendering. A game might have separate threads for physics calculations, artificial intelligence, audio processing, and rendering. But these threads often need to synchronize with each other frequently. They can't just run independently without communication. In this scenario, hyperthreading might provide a modest improvement, perhaps 5 to 15%, but it's not transformative. The game is fundamentally limited by how parallel its code can be, not by how many logical cores are available. There's also a subtle truth that Intel doesn't always emphasize in marketing materials. Those 2 logical cores sharing 1 physical core are competing for the same execution resources. They're not truly independent. The arithmetic logic units, the floating point processors, the cache memory, these components are shared between both threads. If both threads simultaneously need the floating point unit for mathematical calculations, one thread has to wait. The processor is smart about scheduling, trying to pair threads that use different resources, but conflicts inevitably occur. This is why hyperthreading never doubles performance. It improves efficiency by filling gaps, but it can't create execution resources that don't physically exist. Let me share a real-world comparison that illustrates this perfectly. Researchers at a major university conducted tests using video encoding software on a processor with 4 physical cores. With hyperthreading disabled, the processor appeared as 4 cores and completed the encoding task in approximately 10 minutes. With hyperthreading enabled, presenting 8 logical cores, the same task finished in roughly 7 minutes. That's a 30% improvement, significant and valuable, but nowhere near the 100% improvement you get from actually doubling the physical core count. The logical cores helped fill idle time and kept the processor busier, but they couldn't overcome the fundamental hardware limitations. The technology has evolved considerably since its introduction in 2002. Early implementations had more overhead and less sophisticated scheduling. Modern processors from the 2020s incorporate refined versions of hyperthreading with better thread management and reduced performance penalties when threads conflict. Operating systems have also improved their understanding of the difference between physical and logical cores, making smarter scheduling decisions about which tasks to assign to which threads. The whole ecosystem has matured together. Intel's marketing sometimes blurs the distinction between physical and logical cores, listing total thread counts prominently while mentioning physical cores in smaller print. A processor advertised as having 8 cores might actually have 4 physical cores with hyperthreading. For average consumers shopping for a laptop, this distinction might not matter much. For professionals making purchasing decisions based on specific performance requirements, understanding the difference becomes crucial. 2 processors with 8 threads perform very differently if one has 8 physical cores and the other has 4 physical cores with hyperthreading. There's a philosophical lesson embedded in this technology that extends beyond computing. Hyperthreading succeeds not by adding more capability, but by using existing capability more intelligently. How often in life do we seek more resources, more time, more money, more help, when the real solution is using what we already have more efficiently? The processor doesn't work harder with hyperthreading enabled. It works smarter, eliminating waste and maximizing the value of every component already present. Consider your own daily routine. How much time disappears into gaps between tasks, moments of transition where you're not quite finished with one thing, but not yet started on another? What if you could identify those gaps and fill them with productive activity, not by working longer hours, but by reducing idle time? That's the human equivalent of hyperthreading. The chef who preps vegetables while water boils for pasta. The writer who mentally outlines the next paragraph while typing the current one. The student who reviews flashcards during the commute. These aren't examples of doing more work. They're examples of eliminating waste from existing work. The technology also reminds us that perceived capability and actual capability can differ significantly. A processor presenting 8 logical cores appears more powerful than its 4 physical cores suggest, and for certain workloads, it genuinely delivers on that promise. For others, the illusion fades and the hardware limitations become apparent. In our professional lives, we sometimes encounter similar situations. Someone with an impressive title and apparent authority might lack the fundamental skills or resources to deliver results. Conversely, someone with modest credentials might leverage what they have so efficiently that they outperform expectations. The appearance of capability matters, but the efficient use of actual capability matters more. As we wrap up this exploration, think about your own computer for a moment. Whether it's a laptop for school, a workstation for creative projects, or a gaming rig for entertainment, hyperthreading is probably working quietly in the background, squeezing extra performance out of silicon that might otherwise sit idle. You've never seen it. You've probably never thought about it. But it's been there, making your experience slightly better, your renders slightly faster, your compilations slightly quicker. That's the nature of good engineering. The best solutions often work invisibly, improving our lives without demanding recognition. Thank you for spending this time exploring the hidden mechanics of modern computing with me. I hope this story has given you not just technical knowledge, but also a fresh perspective on efficiency and resource utilization. If you found value in this content, please consider subscribing to our channel. We bring you stories that illuminate the technology shaping our world and the lessons we can draw from understanding it deeply. Take care of your health, make the most of what you have, and remember that sometimes the smartest move isn't adding more power, it's using existing power more wisely.